Welcome to you in my channel Mathematical Clinic of Subash. We are in the third lecture of limits and continuity. Today we are going to establish the limit theorem. Limit x approaches to a x to the power n minus a to the power n divided by x minus a equal to n a to the power n minus 1 for all rational number n. Q is the set of rational number and here n is the rational number 1. For any rational number 1 this result holds. That's we are going to establish. To establish this result 1, we will have to discuss 2 or 3 important things. First thing is, what is the rational number? What is rational number? N is a rational number means what? N is a rational number means n can be written in the form P upon Q satisfying two conditions. First condition, Q is not equal to 0, and second condition 1, P and Q both are integers. Integers means this set 1, 0, 1, 2 and so on, likewise minus 1, minus 2 and so on, this set 1. Getting it? Once again I am going to tell you, n is a rational number means the definition of rational number is a number n is called a rational number if n can be written in the form P upon Q, where Q is not equal to 0 and P and Q are integers. For example, can you say 2 is a rational number? Of course you can say, because 2 can be written as 4 upon 2. Can you? By various way you can write 2 as numerator upon denominator. This is in the form P upon Q. Now let us check the conditions 1. What's in place of Q? Q equal to 2 here. That is not equal to 0. First condition is satisfied. Second condition, P equal to 4 and Q equal to 2. Both lie in this set 1. P equal to 2. In place of P it is 4 and in place of Q it is 2. Both 4 and 2, P and Q lie in this set 1. That is why second condition is also satisfied. So 2 is a rational number. But can you say root 3 is a rational number? You can't, because you can even write root 3 as 2 root 3 divided by 2. Can you? Of course you can. Root 3 can be written as 2 root 3 upon 2. This is also in the form P upon Q, where Q equal to 2 not equal to 0. First condition is satisfied here too. But Q equal to 2 is an integer lie here. But P equal to 2 root 3 is not an integer. This number P does not lie in this set. So second condition is not satisfied. That is why this is not a rational number. Rather this is an irrational number. Now I hope you are quite clear about rational number 1. Here n is a rational number. Rational number means n can be written in the form P upon Q, where P, Q are integers and Q is not equal to 0. Actually, we classify rational number into 3 groups. Actually, positive integers, these 1, 2, 3 and so on, all are rational number. Even negative integers, minus 1, minus 2, minus 3, all are rational numbers. Even the fractions, 1 upon 2, 1 upon 3, likewise all are rational numbers. Even decimal number, 0.1, 0.002, this type of number are rational number. Even this can be written as 1 upon 10, like this. So let us classify a rational number n in 2 groups. First one, positive integer. Second one, negative integer. And third one, fraction. Once again from the beginning, a rational number is that number which can be written in the form P upon Q satisfying these two conditions 1. And a rational number can be kept in 3 groups. First group 1, positive integers. Second group 1, negative integers. And final group 1, these two can be combined together and can be called fraction 1. Fraction 1. So we'll prove this theorem in, here n is also a rational number. So we'll prove this theorem in 3 cases. First of all, we prove the theorem LHS equal to RHS when n is a positive integer. Thereafter we prove the theorem when n is a negative integer 1. And finally we prove the theorem when n is a fraction 1. And one more thing required for this theorem 1 is, what is the factor of x square minus a square? What are the factors of this? First factor will be x minus a and second will be x plus a. What will be the factor of x cube minus a cube? This becomes, first factor is again x minus a, second becomes x square plus ax plus a square. On this manner, what will be the factor of x4 minus a4? Actually here also x minus a, here also x minus a, so here also x minus a comes. Now we can consider here the power of x is in descending order. Here power of x is 2, thereafter power of x is 1, thereafter power of x is 0. No x here, that is why power of x is 0. And power of a is in the ascending order. Here a to the power 0, thereafter a to the power 1, thereafter a to the power 2. On that basis, what will be the result here? Power of x will be on descending order. Here it is 4, that is why we start from 3. Thereafter x to the power 2, thereafter x to the power 1, and at last x to the power 0. Thereafter power of a will be on ascending order. First a to the power 0, thereafter a to the power 1, thereafter a to the power 2, and finally a to the power 3. And all terms will be connected by plus. This is the mechanism of finding factor of x to the power n minus a to the power n. On the basis of that, we can say that what will be the factor of x to the power n minus a to the power n? This is not other than, here also x minus a. Power of x will be on descending order, that is why x to the power n minus 1 here. No a here. Now x to the power n minus 2 in descending order. After n minus 1 it is n minus 2. But power of a will be on ascending order. Here a to the power 0. Here a to the power 1. Thereafter power of x will be in descending order, n minus 3, and a in ascending order, a to the power 2, and so on, and finally a to the power n minus 1. This formula will be used while proving this theorem 1. Now let us prove the theorem. Once again, I am going to write here the theorem. The theorem 1 was limit x tends to a, x to the power n minus a to the power n divided by x minus a equal to n a to the power n minus 1, where n is a rational number. First case, as I told you, first case 1 is when n is a positive integer. Let n belongs to set of positive integers. Z plus is called set of positive integer. When n is a positive integer, the value of LHS becomes limit x tends to a, x to the power n minus a to the power n divided by x minus a. Here limit x tends to a as it is, and for this one we had just written the formula 1, factorization formula 1 was the factors of x to the power n minus a to the power n. It is x minus a, thereafter x to the power n minus 1, thereafter x to the power n minus 2a, thereafter x to the power n minus 3a squared, and so on up to a to the power n minus 1. We had just written on next place, divided by x minus a as it is. X minus a will be cancelled. Now substitute x equal to a in this term. If you substitute x equal to a here, then it becomes a to the power n minus 1. This one becomes a to the power n minus 2 into a. This one becomes a to the power n minus 3 into a square plus and so on up to last term 1 is a to the power n minus 1. Here a to the power n minus 1 as it is, by the rule of indices, same base in the form of product. So this power 1 will be added to this one and result becomes again a to the power n minus 2 plus 1 becomes how much? N minus 1. Third term becomes a to the power, again same thing, by the rule of indices, same base in the form of product, so powers will be added, n minus 3 plus 2 will be again n minus 1. Each term will be a to the power n minus 1. And how many, actually each term is same. And how many such terms are there? There are n such terms. If you add two same terms, then answer will be 2 into a to the power n minus 1. If 3, then 3 into a to the power n minus 1. But here n such terms are given, so the sum becomes n into 1, n into a to the power n minus 1, and this is the RHS one. So we have proved the theorem when n is a positive integer 1. Move to second case 1. Let us suppose n as a negative integer. Suppose n is a negative integer 1. Now let us consider some negative integer. For example, minus 2 is a negative integer, minus 3 is a negative integer. Can you say that a negative integer can be written as minus multiply positive integer? Of course you can, because minus 2 can be analyzed as minus. If you keep minus outside, then plus 2 is the positive integer. So every negative integer can be written as minus multiply positive integer. Here n is also a negative integer, so n can be also written as minus multiply positive integer. Suppose that positive integer is m, where m is a positive integer, because every negative integer can be written as minus multiply positive integer, and here n is also a negative integer. This can be written as minus m, where m is a positive integer 1, minus times positive integer 1. Now what's our LHS? Our LHS is limit x tends to a, x to the power n minus a to the power n divided by x minus a. Let us replace n by minus m. This becomes the limit x tends to a, x to the power minus m minus a to the power minus m divided by x minus a. By the rule of indices, this can be written as limit x tends to a as it is. This x to the power minus m can be written as 1 upon x to the power m. And this a to the power minus m can be written as 1 upon a to the power m divided by x minus a as it is. This is limit x tends to a as it is, and here we are taking LCM. X to the power m into a to the power m will be LCM. On the numerator it is a to the power m minus x to the power m, and divided by x minus a can be written here x minus a. This can be written as limit x tends to a as it is. We are taking minus common from both of them. Then the result becomes x to the power m minus a to the power m divided by x minus a is kept here, and remaining 1 upon x to the power m into a to the power m here. This equal to minus as it is, and cos m is a positive integer, and we have already proved the theorem for m. That theorem can be applied here. To apply the theorem means the theorem was limit x tends to a, x to the power n minus a to the power n by x minus a equal to n a to the power n minus 1. The mechanism one is you multiply by the power is same here n, and write second term as it is and subtract 1 from the power. Here also m is a positive integer, so you can apply, and you have proved the first class for the positive integer one. Here you can apply the theorem. So you multiply by power is m here, second a to the power m as it is, and you subtract 1 from the power 1 into here 1 as it is. In place of x you are going to substitute a, it becomes a to the power m, and this one is a to the power m as it is. Let us apply the rule of indices here. Minus m as it is, a to the power m minus 1 as it is. If you take this a to the power m on numerator, it becomes power minus m. By the rule of indices, they are in the division and having same base, so power will subtract, m will go upward being minus m, and this m also minus m. M and m cancel, so you are left with minus m into a to the power this one minus m and this one minus 1. And as you know, what is minus m? Minus m is n, because here you have substitute n equal to minus m, so minus m can be again replaced by n, so it is n, and a to the power again minus m is n minus 1. This is the RHS. So we have proved the theorem in two cases. Now let us move to final case 1. The final case 1 is case third. I had told you there are three cases. As n is an rational number, it can be positive integer, negative integer. That cases have been proved, and now we are left to prove in the case n is a fraction. Let n equal to fraction. Suppose n equal to p upon q. Q is not equal to 0, you know, because it is a rational number, and p and q both are integers here. Then again write the LHS. Our LHS is limit x tends to a, x to the power n minus a to the power n divided by x minus a. We are going to replace n by how much? P upon q. So the result becomes limit x tends to a, x to the power p upon q minus a to the power p upon q divided by x minus a. Here limit x tends to a as it is. I am going to write this x to the power p upon q as x to the power 1 upon q to the power p. Can you? You can. because if the power is there, then power will be multiplied and it becomes p upon q. And here also this a to the power p upon q can be written as a to the power 1 upon q to the power p. I am going to divide this result by x to the power 1 upon q minus a to the power 1 upon q. Here denominator is x minus a. This can be written as, this x can be written as x to the power 1 upon q to the power q. Can you? Because q and q will be cancelled and you will be left with x. And even a can be written as a to the power 1 upon q to the power q. Again q and q will cancel and you will be left with a. Because you have divided the numerator by this one, you have to divide the denominator by that one also. X to the power 1 upon q minus a to the power 1 upon q. Actually we have done this. We have divided both the numerator and denominator by this factor to apply the formula here. Here also you can apply the formula, and here also you can apply the formula, because p and q are positive, integers, and for the integers we have already proved the theorem. Let us apply the theory here. If you apply theory here, then what will be the result? You multiply by power. Power is p in the numerator. A to the power 1 upon q to the power p as it is. You subtract 1 from there. That's the mechanism of the theory. You multiply by the power, second term as it is, thereafter you subtract 1. Here also you multiply by the power, second term as it is, thereafter you subtract 1 from there, from the power 1. Do same thing here in the denominator. It becomes, you multiply by power, power is q, second one a to the power 1 upon q as it is, even to the power q as it is, you subtract 1 from the power. So the result becomes p upon q as it is. Here a to the power, let us multiply both the term by 1 upon q, it becomes p upon q, and 1 upon q here, then minus 1 upon q, divided by a to the power, here q upon q is 1 minus 1 upon q. Again by the rule of indices, p upon q as it is, it becomes a to the power p upon q minus 1 upon q minus 1 plus 1 upon q. 1 upon q will cancel. You will be left with p upon q a to the power p upon q minus 1. And cos p upon q is how much, n? This result becomes n into a to the power n minus 1. And that's the theorem. We have proved the theorem in all the cases. That's all.